Okay, so this is lecture 5. Still we are working on diffusion, and in the previous lecture we have introduced how can we solve steady state diffusion equation and also time transient diffusion equation for one species. So today we will talk about what will happen if we have to consider multiple species, and also how to consider the electric field effect in our calculation. So this is about boundary condition. So do you remember our previous boundary condition? So previously we thought that there is a certain left boundary and right boundary, and we thought that the initial condition for initial density for these 2 points are just fixed. I mean that, so C over x equal to 0 and anytime t is equal to C over x equal to 0 and the initial time instance. You have also thought about this one, the right boundary. Still we have the same value at time equal to 0, the initial one. So previously we have thought about that one. So it is good when we consider such kind of behavior. Okay, our initial dopant distribution is concentrated on certain range. After that, if we apply certain heat, then it will be diffused. However, the boundary, they are far from this center of our dopant profile, so it is always good to assume this kind of thing. However, think about more realistic situation. The more realistic situation is we have very thick, relatively thick system called vapor. However, actually we are working on the surface area only. So simply speaking, although we have a certain system, but we are only working on this very shallow region of our silicon vapor. So now let's magnify, and this is the one. In this case, if we have a sufficiently thick simulation domain, then still we are free to say, okay, this concentration doesn't change because our dopant is located here, and even after certain diffusion, it cannot reach this point. So it's good. However, please note that even the initial profile have some non-negligible values at this point. So typically what we can expect is like this. This is typical doping profile as implantation is over. So here we have non-zero profile even at the surface. Then what will happen? If we apply certain heat, then it will diffuse in this direction and also that direction. So usually what we have is as time goes, then increase of our dopant density. Okay, so are you with me? So it is very difficult for us to decide the value at this point. I mean that previously we just set the value of dopant concentration at both boundaries, but right now I'm saying that for x equal to 0 corresponding to the top surface, it is difficult for us to determine the value itself. So what is it? We have no idea. Then instead of that, what we can have is, for example, this is just an example of possible boundary conditions. For example, let's say that this boundary is regarded as a hard wall. So dopants are diffused over this reaction. After that, when it hit this boundary, it cannot escape from this top surface or this vapor system. If we have such kind of thing, then the assumption we can have is, okay, so flux of our dopant concentration should zero at this top surface. This can be another boundary condition we can apply. So this is a Neumann type boundary condition instead of a Dirichlet type boundary condition. So I would mean, so Neumann boundary condition just to describe something like this. What is gradient or derivative of our concentration? This is Neumann type, and if we say something about its value itself, then this is called as a Dirichlet type boundary condition. Also, when we have number 0 here, then we have no external term, then this is called as homogeneous Neumann boundary condition. And if we have a non-zero value, then we say inhomogeneous Neumann boundary condition. So right now, we will consider the boundary condition about flux is vanishing. So in this case, flux is directly related with this gradient of density. So we will apply, in other words, homogeneous Neumann boundary condition to our top surface. So are you all with me? So simply speaking, in the previous lecture, we have applied Dirichlet boundary condition for both ends, I mean that x equal to 0 and x equal to n. But today, instead of that, we will apply the Dirichlet boundary condition only at x equal to n, and for x equal to 0, we will apply homogeneous Neumann boundary condition. Okay, so then how can you do that? That is my question. How can we set this boundary condition? You know that since this is related with the x equal to 0 law, so we have to modify the very first law of our system matrix. So you can easily expect this kind of modification. So let me just directly dive into my conclusion. So if we have the condition, boundary condition about zero flux, vanishing flux at the top surface, then our discretized diffusion equation is written as this form. Of course, everything is exactly same as before, except for this, the very first law corresponding to the boundary node. Of course, here we have another boundary node. However, it is not modified at all. Why? Because still we applying the Dirichlet boundary condition for this x equal to L node, and only difference is shown here. Previously it was 0 and also it was 0, so identical to this way. However, now we have seemingly quite strange values like number 2 and number 2, minus 2 and positive 2. So how can you justify the use of these values? Well, At first glance it looks quite strange. So minus 2 is taken from this minus 2. Okay. But still, this off-diagonal component had just number 1 previously, but now I'm using number 2 instead of number 1. So my question is why we have such kind of seemingly quite strange behavior. Do you have any idea about why we have this kind of behavior? Okay, so we'll give you the answer about the boundary condition. Okay, so anyway, please note that since we are now modifying the boundary condition, so our system should be also modified. However, the modification is just localized at the given boundary node. Okay, then answer is quite simple. Integration. Let's consider our original equation. So our original equation is written as this one. So time derivative of our concentration is balanced with second derivative with respect to the real space. So now previously it was done, and the left hand side, so left hand side term was discretized by what? Taking the backward Euler scheme. So when you come back, you can easily understand this is corresponding to the backward Euler implementation of your round C over round T. So taking the difference of your C value and divide it by the time difference between Tk and Tk minus 1. That was so easy, and we are going to this right hand side, and right hand side is related with this second derivative of our C. Then it was discretized with this 1 minus 2 1. So this is implementation of our Laplacian second derivative, and this is augmented by our boundary condition. That was our previous setup for our system AX equal to B. And now I wanted to give you how can you do it systematically for this case. The key is integration. Integration over what? Integration over, oh sorry, so sometimes my pencil is lost. So in this case I have to wait for a while. Okay, it works. However, my pencil, okay, now. So integration is required, and integration over x value or real space value is required. Then let's just try to integrate our equation left hand side, right hand side in both cases over a certain range starting from x minus, this is lower bound, and x plus, this is upper bound. Then let me just do it together with you. So round C over round T, and that is integrated from x minus to x positive. Then what will happen? In this case, real space and time domain can be interchangeable, so we can just put our time derivative in front of this integration, real space integration. So it is not that difficult. So that's the reason why here we have the term like this. First, we integrate our C values over certain range. Who decide this range? So we can decide this range. But anyway, we integrate our concentration over given range and taking the derivative of this one. Okay, that is the first one, and the left hand side. Then let me just do the second one, the right hand side together with it. So it is not very difficult. So here we have D and round C here, and of course please note that we have already assumed that D is constant over our system. So that's the reason why we have actually D in front of this derivative. Then we can also pull it out. Then remaining thing is amazingly simple. So just to round C over round X, first derivative with respect to X and evaluate at X positive. The upper bound minus round C round X evaluated at lower bound. That is my explanation. So now you have exactly the same thing here. So it looks quite simple, but what is the relation between this simple integration and our boundary condition? Please have a look at. So in the case of just a normal node, so not like x0, so let me just do, let me make a case study. For example, x1. x1 is nothing related with the boundary. So here we have x0 and x1 and x2, and their distance is denoted delta x and delta x. That was our previous assumption about this uniform grid. So if we adopt this kind of grid structure and apply some case like this, x minus is taken as just half delta x. Okay, then x positive is given by 1.5 delta x. So are you with me? In this case, I'm just saying that for x sub 1, we are taking the integration range for these two boundaries. Okay, so what is x minus selected in this case? X minus written as 0.5 times delta x just shows the midpoint between x0 and x1, and x positive shown here is just showing the midpoint between x1 and x2. If we take this kind of description, then let me just explicitly write down our quantities round t and integrated from 0.5 delta x, 1.5 delta x, and c and dx. And you know, this quantity, this real space integration centered at x sub 1 is actually represented by which quantity? So the quantity at x equal to x1. Everybody understand this quantity is well represented by its center value x plus 1. Of course, there is difference in unit. What is it? The upper one is integrated c value, and this one is just c itself. So in order to match the unit dimension, we have to multiply also this length scale. Then what is the required length scale? The length scale required here is simply the difference between x plus and x minus. So are you with me? If we have, for example, let's say x and c value is varying function, position dependent varying function, and we have x1, and this is our x minus, and this is x plus, and we have to calculate the area underneath this curve. Then how can we calculate this integration? We are now saying that instead of taking the real integration, just taking the representative value here and multiply the span of our integration range. So this is given by x plus minus x minus, and this is the c value evaluated at x equal to x1. So this is just a way we integrate. Of course, in reality, in mathematics, we have to make our x plus and x minus quite close to x1. However, we have limited capability to approaching 0. So instead of that, we have made a simple approximation, taking the representative value and multiply the length of our integration domain. So now this one can be well approximated by this one. And what is it? X plus minus x minus was delta x. So now we understand the left hand side term. Oh, sorry about that, still okay. So left hand side term, now after taking this integration over small area, then that can be written as a round over round t, and c x equal to x1 times delta x. This is the integrated form of our integral of diffusion equation. So are you all with me? Now, if you are happy with this one, then let me just move to the right hand side, and it was integrated over small range centered at x equal to 1, x equal to x1. So let me just go to the left hand side, right hand side. Now we have to calculate this quantity, round c over round x, evaluated at x positive. What is x positive in this case? This is the midpoint between x1 and x2. So it is really well approximated as c x2 minus c x1 divided by x2 minus x1. So are you all with me? So also this is written as also delta x. Then let me just do the second term, d times round c over round x evaluated x minus can be also written as x1 minus x naught, c evaluated x1 minus c evaluated x naught. And as you can see, still this difference between x1 and x0 was taken as delta x. Then let me just collect them all. Then when you collect them all, the right hand side can be written as d times overall delta x and c x2 minus 2 times c x1 plus c x naught. Please have your time to check whether my evaluation is correctly done without any mistakes. So if you accept all of my derivation, then let me just make the balance between left hand side and right hand side. I think that we can do it quite easily. Let me just do it. Since the left hand side is written as round t over c x1 times delta x, I'm just to write down the left hand side, and I'm just to write down the right hand side here. delta x c x2 minus 2c x1 plus c x naught. Then I wanted to ask you, what is the difference between my form finally obtained by equating the left hand side and right hand side and our previous implementation? For example, you can understand we are now talking about the second law here. Second law is here because we are talking about the equation evaluated at x equal to x1, and that is corresponding to the second law. And what is the difference between our current implementation and our newly derived equation? Here we have just round over round t of our concentration, but here we have something annoying, so delta x. So in order to match it, then why don't we just delete this delta x and put it here? Then we will have this form. Then you can immediately find that this blue boxed equation is actually the one we have done in our previous lecture. So simply speaking, although that looks a little bit complicated, but my suggestion is first taking the integration of our original equation over certain range, then we will get the same expression for our discretized equation. So that is my first suggestion. Why we are doing such kind of a complicated thing? The reason is it gives us a general way to treat even non-uniform spacing. So I mean that instead of x equal to x1, now let's consider x equal to x0. Wow, then what will happen? Even in this case, we can integrate our equation. Then in this specific case, what can be the integration area or integration domain? We have the leftmost point called as x0, and here we have a right point x1 and x2. Previously, when we consider the x1 as a center point, it was quite easy, taking the midpoint and midpoint for surrounding 2 points. But you know, in this case, if we have to consider certain integration for x naught, then what is your suggestion about the integration range? The integration range should be, as all of you can quite easily expect, is starting from 0 and ending at half of delta x. I mean that this red shaded area should be the integration area for our center node x sub 0. Okay, so are you with me? So some of you can say that, okay, why don't you just introduce integration over this one? However, please note that our simulation domain starts from x naught, so we cannot expand our integration range over negative x values. So please note this one. So that's the reason why our integration range is somewhat reduced. Previously, we have integrated over a range with length delta x. However, now we have integrated it over just a half length. Then what will happen? In this case, now let's do it. In this case, since we all have done it already, so now we will have just half length, okay, for our x0 quantity. So if you have any question, then please let me know. The left hand side just to have half length, so we have to multiply half length, and the center point is now no longer x1, instead it is x0. And the right hand side, now we have to calculate these two considerations, these two quantities, evaluated at upper boundary and evaluated at lower boundary. Upper boundary, it is still okay because we can take the difference between x1 and x0 and x1 and x0, and this difference is still delta x. But please have a look at the one evaluated at the lower boundary. What is the round c over round x evaluated at x minus lower boundary? That cannot be approximated by this kind of first derivative because we have no idea about what is it using just unknown variables. We have to say, with the help of our boundary condition, this is 0. Who say this is 0? Just boundary condition tells us that the round c over round x evaluated at x0 should be 0. So by taking this boundary condition, then our right hand side term can be evaluated in this way: x1 and x0. They are taken from the upper flux, and we have no lower flux, and that's it. Okay, so are you all with me? So this is just the integrated diffusion equation, however, that is centered at x0, the boundary node, and we have applied the boundary condition already. So that blue boxed one is now the suitable discretized form of our diffusion equation. Then finally, let's do the same thing. Still, that looks quite annoying, so let me just eliminate it. Then delta x becomes, as usual, square of delta x. But please note that here we have additional half, and this half goes here, goes here. So now we can safely eliminate this form. Wow. Then if we just write it down in a form of a matrix, then we can immediately find that this is the form we have to have in the case of the top surface boundary. Okay, so please have your time to think about all kind of this procedure. So by taking this quite general and systematic way, we can easily apply the boundary condition into our system. So looks quite good and sounds great. So later you will find that we can expand this kind of technique to even multi-dimensional cases. I mean that right now we are talking about just a one-dimensional system. However, this technique can be expanded to two-dimensional or even three-dimensional system without any difficulty. Okay. So do you have any question?
적분 구간이 델타 x에서 2분의 델타 x로 줄어들었다는 말씀이죠.
Yeah, you're right. So we have reduced our integration range, and even in this reduced one, we need the flux at this point and that point. However, with the help of a boundary condition, we can eliminate the contribution from this leftmost flux. Okay, so that is the way we adopt our boundary condition in our into our discretized equation. Okay, that is quite a useful technique used for many cases, except for when we consider directly boundary condition. Okay, then let's go to our simulation result. Simulation result is, previously we have thought about the initial profile, the delta-like profile, and it was diffused over along positive x direction and negative x direction. So I made just a half a program. So initially a Dirac delta-like profile was introduced. However, those was just half of it. Then we apply the boundary condition like zero flux. Therefore, previously our solution was looked like this. However, now we are just having the half of it, and it is diffused only along the positive direction. Then you can also do it with the same parameters. Are you with me? So you are now looking at the solution at 400 after 400 seconds, 16, 3600 seconds later, and you can easily find that this is corresponding to your previous solution. Take just half of it. Okay. Of course, you have to use the same parameters. So I wanted to ask you, please implement this one. Only difference is now you have to introduce different boundary condition. Previously, you had not care about these components. I don't care about this component. But now you have to introduce these two components. Then after that, you will get very beautiful, still Gaussian shape, half of a Gaussian shape in this case. Okay. Do you have any question about this homework number 5? So you have to be able to calculate this profile. Okay, if you don't have a question, then let me just move to the next topic. Up to now, we have thought about the diffusion of boron atoms or arsenic atoms, phosphorus atoms. However, in reality, in the silicon, we have multiple species. For example, in order to make a p-type, so let's say that this is a concentration and this is real space, then usually in order to make such kind of a p-type junction, p-n junction, for example, you apply such kind of a behavior. Oh, this is your p-type dopant, and you also make such kind of thing. So this is your n-type dopant. After that, you apply certain heat. Then we cannot say like this. Okay, please hold on. You are not allowed to diffuse. Only n-type can be diffused. It is not possible. So when you apply certain heat to the system vapor, then both of our p-type dopants and n-type dopants, they are all moving together. So unfortunately, we have to be able to consider multiple species, so multiple atom types in the dopant simulation. So think about this one. In order to make a p-n junction, so in order to make a p-n junction, we have to typically adopt this kind of boron and arsenic, or boron and phosphorus, but usually arsenic is more preferably used for N+ reason. So we have boron and arsenic. Then if we have to consider the diffusion of these two dopants, then how can we do that? Of course, we may have two different approaches. One is calculate each of them individually. For example, let's say that we have done it with 60 minutes long, then just to diffuse boron 60 minutes and arsenic 60 minutes, then just to make a sum of them. However, everybody can understand this is really ridiculous and not suitable for realistic case. In the realistic case, they will be interacting to each other. The existence of boron and arsenic will affect to the others simultaneously. So this is not a good idea. Of course, in our highly idealized case, then it's okay. However, please note that this is not general. Then the natural way is, the only natural way is calculate both of them simultaneously. And how can we do this simultaneous calculation of our dopant diffusion? So since we are now considering both of them simultaneously, the solution vector should be twice larger. Previously, we have considered only concentration of boron or concentration of arsenic. However, now our solution vector should consider both of Cb, boron concentration, and C, arsenic simultaneously. Let's say that there was n unknown variables. Now we have to consider 2 times n unknown variables. So simply speaking, our computational burden will be increased by introducing these cases. However, we are now considering more complex system. Therefore, we have to spend more computational efforts to solve this one. That is quite reasonable. And I wanted to raise one issue about arranging of unknown variables. So in this simple explanation, I write down in this way: Cb, first Cb, after that later C arsenic. Then it means that Cb x naught, Cb x1 up to Cb n minus 1, xn minus 1. Once after Cb are arranged and taking the first n entries of our solution vector, after that we can introduce C arsenic, x naught, something like that. So ending at the xn minus 1. So this is written here. This just shows that our solution vector first consider Cb, boron concentration. After that, arsenic concentration comes in. It sounds quite reasonable and good, but usually we prefer to have this position-wise arrangement. Please have a look at this one. In this case, first we consider a given position and collect all of available solution unknowns. I mean that here we have Cb and arsenic concentration at first node or zeroth node, and for first node we have Cb, C arsenic, something like that. Then our instead of this kind of behavior, so neighbors are more or less having the same type and same type. Now in this new alternative way, so neighbors are placed in a same position or nearby position. So this is more based on some position-wise closeness, and this one is more based on the similarity of your species. Okay, so however, I want to say that this is more preferred way of implementation. Why? You will see later. But anyway, so now you have another example. Now consider boron and arsenic dopant diffusion. So initially you have this kind of arsenic dopant profile, and this is boron dopant profile. Please note that this is initial one. I mean that time equal to 0. And your goal is to calculate 60-minute long anneal. So what will happen if we anneal over for 60 minutes? Then please note that here we have boron concentration, and it is centered at this 0.5 micrometer. Peak density is shown here also, and standard deviation is 50 nanometer. That is describing this boron uh, concentration. And second line, arsenic concentration peaked at 0.2 micrometer, and peak density is 2 times 10 to the 20. Standard deviation is 250. Oh, so I'm sorry about that. I'm not quite sure. So I think that I have to change it. So I will repost my my corrective standard deviation. So please note that if you take this 250, then it will be much wider than this one. Sorry about that. I will fix this value and post it once again in our GitHub repository. Okay. So anyway, please consider this kind of initial arsenic and boron concentration. Then you have the second homework. Draw the final dopant profiles in the linear scale. What's the linear scale? So x and y, both of them are written in linear scale. That is my linear scale. And please draw the same dopant profile in the semi-logarithmic scale. Means that sometimes this kind of concentration is very difficult to understand written in this linear scale. So please take the log 10 based axis for only for this y-axis. Please keep the linear scale for real space position. Okay, so are you with me? This homework number 2 is devoted for your effort to implement multiple species problem. So later you should be able to include many different species into your system and consider all of them. Of course, I wanted to recommend you to take this kind of arrangement. So of course, it is okay, or it would be easier for you to take this kind of arrangement for your implementation. However, when your implementation becomes easier, then your computer will spend more computational resources to solve that problem. So it is my suggestion to take this first possible implementation, like proximity based arrangement. So then what happens? So for example, now you have to consider this kind of a problem. CV that is given by boron diffusivity and second derivative of boron. Okay. At the same time, you have to also consider arsenic concentrations time derivative is balanced as also second derivative of arsenic concentration, and they should be implemented. And the point is the second derivative of this real space. Then how can you consider this one? Then I guess that you have to have something like this. Let's say that here you have 0, 1, 2, 3, 4. You know, this is the node for your x equal to x1 and for CB. And you have a second another line like position is still x1, but you have to consider arsenic equation. Are you with me? So since your solution variable also having such kind of a behavior or arrangement like CB at x1, CAS x1. Later you have CB x2, CAS x2. Your equation should be also arranged that way. First, your first law should be x equal to x naught for CB and x equal to x naught for C arsenic. This one. Okay. Do you have any question? Yes. If you have any question, then please interrupt me.
이거를 제가 조인트하게 풀어야 되는, 그러니까 따로따로 안 풀고 조인트하게 풀어야 되는 이유가 조금.
Okay, that is a good question and I already explained it, but I will repeat this one. So you are now talking about this first one. So calculate them individually. So actually in this system, boron and arsenic are not interacting anymore. So it is completely okay to take this first one. But later you will find that even in this case, although boron and arsenic are different, but they are interacting with many different ways. So we will learn why they are interacting later. But right now, although they are not interacting particles, but for our future use, we will just make something like that. It's like this. I mean that. So let's say that you are a middle school student and you are asked to solve this problem. X plus y equal to 1. X plus 2y equal to 2. And g plus w is 3 and g is 2, w is 3. If you have this kind of a problem, you are all educated and you immediately find that, okay, so although we have 4 different variables, but they can be subgrouped like x and y and g and w. So since they are not interacting anymore, so we can subdivide this system into 2 pieces and we can solve a small problem and small problem. That is educated student. However, let's say that I just introduced one term like z here and I added something like y here. Then what will happen? Then immediately this division becomes impossible and we have to consider the full system. Right now we are considering this red colored system, but later we will include this kind of interaction terms. That's the reason why we are currently making the 4x4 matrix for them, not taking two pieces of 2x2 systems. Okay, that was a good question. So motivation was for our future use, and in this case, now since we are talking about the second derivative of our CB, then what will happen? In this case, you can immediately understand we will have some terms like 1 minus 2, 1 here. So are you all with me? And also we will have 1 minus 2 and 1 here. Because you know this guy is corresponding to C arsenic. and this guy is also corresponding to C arsenic. We are not talking about C arsenic derivative in this equation. So this equation will take just this kind of discretized values, and at the same time for equation arsenic concentration, then we have nothing related with C boron. So they will be the zero entries, and we have just common 1 minus 2 1 things. Okay, so seemingly quite easy, but when you actually try to implement, it is very error prone. So easily you can make many errors, because at the first time, just to make a single mistake in multiplying some number 2 or positive 1 minus 1 will give you a crashed result. So please don't make any mistakes and make a successful homework problem number 2. Then how can you verify your result? What is your opinion? How can you verify your multi-species simulation is okay? I think that one straightforward way is just to run twice your single species problem and use it as your reference. If your multi-species simulation is well implemented, then you will get the identical result for both of them. Okay. So, any further question? Okay.
저희가 이 문제 풀때
음.
바운더리 컨디션은 어떤 걸 쓰죠?
Oh, sure. Oh, that is really good question. Please use the new boundary condition. So always we have a top surface, and top surface should have really its own important boundary condition. Later we'll talk about also boundary condition at this point. Right now we are now using zero flux or vanishing flux, but actually in real semiconductor process, actually the flux is not zero. So we'll talk about it later, but right now please assume the zero flux at the top boundary. Oh, that was a really good question. I never thought of that, because I just took it as granted. So please take, for while, take this zero flux boundary condition for our top surface.
그러면 그 아세닉 같은 경우에
Okay.
1000나노미터까지 확산이 일어날 수 있어 보이는데.
Okay, good. It's really good. Really good question. So I will always, first of all, I will give you the reduced value for this standard deviation. So it is, yes. So this is the correct one, and you can find that actually the values at here is not exactly zero. It has a considerable value, but if you take this position 1 micrometer as a right boundary, then just to let it be fixed. So then of course, oh, is it really correct? Then you can, one way is you can just extend it up to 2 micrometer and run it fixed at this point. Then what will happen? Then you will have a more accurate value for your boundary value. Compare this value at this extended simulation domain or shorter simulation domain and check the difference. If the difference is not that severe, then we'll be happy. And if that difference is too large, then we have to rethink about extending our boundary. Okay, so always, sometimes students can ask me the question, what is the suitable value of a boundary? How wide it should be? Then we have actually no idea in previous without taking the simulation. So always the condition is, the boundary condition should be reasonable And if we introduce this shorter boundary, then we will introduce some distortion into our solution. The best way would be extremely long simulation domain, but that will increase our computational effort. So anyhow, we make certain compromise, how much we can spend for our calculation and how much we want to get the accurate solution. So if we take, for example, take this 600 nanometer as a boundary, then what will happen? Of course, we will get the solution much faster, and it is obvious that there will be severe distortion in our solution. How about 400? Can you fix at this point and just to let it be fixed even after 1 hour long diffusion? It's not possible. So therefore, your question was really good and really important, and even in this case, arsenic seems to be just expanded up to 1 micrometer. Certainly you will. Then please check for the accuracy or validity of your solution by expanding your simulation domain. Really good question.
그러니까 우측은 디리클레 주고 왼쪽은
Yeah, you're right.
여기서 이게 슬롭이 제로가 되는 것 같은데 지금 제로가 안 되고 있는 건가요?
No. That is also really good question. In reality, we have always non-zero density at top surface.
그러니까 슬로프가 이제 미만 컨디션이니까 슬로프가 제로가 돼야 되는 거예요?
No. Good. Really good question. So I really thank you for that good question. He is now talking about this kind of behavior. Since we are assuming that here we have round C over round X equal to 0, therefore we have to have really flat value at this point. However, it's not. Why? Why it is not 0? It is because here we have something like this. I mean that when integrated, then let me just quickly write down. We will have this kind of thing, D and round C, round X. And of course here we have 0, which was assumed from our zero flux boundary condition. So you can easily find that if we have this flux gradient, then that is balanced by the time derivative of our concentration. I mean that this is a kind of hardware, and particles, dopants are coming. Then what will happen? This point here we have no flux of our particles, but here we have non-zero particles flux. Then we will just accumulation of more and more particles. So we expect that if we take the simulation over a certain time, then we will have the peak is reduced and it is just increased over here, and there will be just accumulation of our particles. So please try to do that, then you can easily find that actually since we have no exit for our arsenic, then there will be pile up over our arsenic atoms. Okay, that is really also really good question. Thank you for your active participation. So I got a lot of important questions from you students. Thank you. Any other question? So I'm quite happy to get your valuable questions. Then already things get a little bit beyond our intuition, so we will find that this kind of subjects are really interesting. So anyway, let's go to this one. Actually, I mean that this graph itself is correct. The only thing I will correct in my presentation material will be the correct value for this standard deviation. Please do your calculation with correct standard deviation. Okay. Then now we will move to the next topic. Now we have diffusion of multiple species, and we wanted to consider the effect of electric field built inside the silicon substrate. That is also an important question. Okay, so I told you that, or he asked me why we have to consider coupled simulation for different species. Actually, this electric field dependence is one of the reasons why we have to consider multiple species. So you know that here we have boron and here we have arsenic, and they are contributing the positive and negative charges. And also, according to their existence, we have also p-type, oh sorry, no p-type, I mean that we have positive holes and negatively charged electrons. They are existing in our system. So, although when arsenic is diffusing or boron is diffusing, also there exists some charged particle like holes and electrons, and from all of them inside our silicon substrate we have the electric field. Then what will happen to this electric field? So let's say that here we have a lot of arsenics and they are positively charged, and there is no arsenic. Wow, then they wanted to diffuse. This is diffusion, but happen to be, let's assume that there is a strong electric field built by some reason. Then what will happen? If we have this kind of configuration, then the diffusion of our arsenic atoms will be reduced by the action of electric field. Electric field push away our arsenic atoms from this point. So that is quite important for realistic cases. So you know why we have this kind of discussion. So let's think about historic behavior. So the macroscopic equation we have studied up to now is quite easy and simple, and by applying that one, they mean that our former engineers tried to match the diffusion profile. However, they failed. Why they failed? They failed because they neglected many effects like electric field dependence, or later electron density dependence, or more effects were not included in their calculation. So since main motivation of all kinds of this discussion is to match the experimentally available data, so we have to consider more and more effect to consider the, the summer diffusion problem. Okay, so are you with me? So up to now we have considered just diffusion. Diffusion is related to just a number of our species. So whether that is positively charged, negatively charged, or even neutral, that doesn't make any difference. However, unfortunately, our atoms are actually ions, so they are reacting against the electric field. Okay, so now let's go to the discussion about drift. Up to now, we have considered only the diffusion term. So flux was written as this one. So this one, the flux, contains only one single term. And what was it? It was originated from diffusion mechanism. However, if we consider a charged dopant ion, so this is the case of our dopant, then the drift should be also considered. I mean that previously we had diffusion term and we must consider also drift term. So simply speaking, say once again our arsenic example. Here we have the region where we have many arsenics and here we have no arsenic zone. Then we will have strong diffusion by diffusion mechanism. But let's say that we have also electric field heading this way, then our arsenic will push it away and that will make certain component made by electric field. So the average velocity only due to this electric field is denoted as V. So actually this is not entire the total velocity, but this is the velocity due to the drift mechanism. So here we have a diffusion term and drift term, and the drift velocity is given by this way. Here we have just a positive sign. So electric field, direction of electric field and direction of electronic or dopant movement is well aligned. I mean that here we have a positive charge. So positive charge and electric field is heading this way. Then we have the movement in this way. But instead of that, if we have a negatively charged particle here and still electric field heading the negative direction, then what will happen? In this case, the direction will be the opposite. They are drained to the source of electric field. So for negatively charged dopant ion, then we will have negative value, positive and negative. Who decide this one? Yes, this is actually the polarity of your dopant ion. So for same case, let's say this one. Here we have arsenic and also same amount of borons are there. Here arsenic and boron. And we have the same electric field. What will happen? In this case, our arsenic, its movement will be just reduced, lower diffusion. And how about our boron? Their movement will be enhanced. So what we can expect from quantitatively is after same time later, and let's say that they have the same diffusivity accidentally, then we will have this kind of arsenic behavior. However, quite much driven boron profile. Okay, because this electric field will enhance the movement of boron. Of course, that is true if we just revert the direction of our electric field, and these two atoms will behave the completely different way. Okay, so we will continue this discussion on Wednesday, but please note that from now on we will consider the effect of electric field. So together with this electric field, the motion of our ionized particles will be heavily affected. Okay, then do you have any question? So if you don't have any question, then I will wrap up today's lecture. Thank you. 네.